Okay, so before we talk about the quantum Fourier transform, let's introduce some basic notions about complex numbers and complex analysis, a subject called roots of unity. So recall that a complex number c can be given in the polar form. So we can write c in its polar form as rho and theta, where rho denotes the magnitude and theta denotes the phase of the complex number c. But for unit length vectors, of course, the magnitude doesn't matter here, so we simply take rho to be equal to 1 if c is of unit length. But in general, suppose that we are not working with unit length vectors and assume that we want to take the nth power of some complex number c. So the nth power of the complex number is denoted by c to the power n, and this can be written as rho to the power n and theta times n. So taking the nth power is basically multiplying the phase n many times if we are working with unit length vectors. So if I have to draw a small figure here, suppose that we have a complex number c, suppose that the angle that it makes with the x-axis is theta, then c squared is basically this vector. So we add the phase n many times, okay, and this is c to the power 3. Again, the angle is theta. Alright, so why is that? So why is it that taking the nth power of a unit length complex number is simply adding the phase n many times? Well, this comes from trigonometry. Suppose that we are working on the unit length circle on which we are given two complex numbers, x and y. Suppose that x is written in trigonometric form. So x is cosine theta 1 plus I sine theta 1. And in the exponential form, this is written as I theta 1. Suppose we have another complex number y equals cosine theta 2 plus I sine theta 2. So then x times y can be written as cosine theta 1 plus I sine theta 1 times cosine theta 2 plus I sine theta 2. We can take the cosine parentheses and then take the I sine parentheses afterwards. Well, this is simply equal to I to the e to the power I, the phases added together. So then multiplying, taking the nth power of a complex number is simply adding the phase n many times, okay, if it's of unit length. Okay, so let's now consider the nth roots of complex numbers. Given a complex number in the polar form, its nth root is the nth root of c is c to the power 1 over n, and this is rho to the power 1 over n times theta. But notice that if we look above, the phase of a complex number is actually defined up to multiples of 2 pi, right? Because if we go beyond, it cycles, it repeats. So the phase is defined up to multiples of 2 pi, so therefore we can rewrite this equation as rho to the power 1 over n. And then we have 1 over n times theta multiples of 2 pi, so that's 2k pi. Now, it turns out that there are, in fact, several nth roots of a complex number. Now, we ask the question, well, how many different solutions are there given a complex number c? How many roots are there? So we get different roots of a complex number by giving different variations to this variable k. And it turns out that there are exactly n many nth roots of complex numbers. There are exactly n many nth roots for a complex number. So let's see how it works. So we give k, let's suppose that k is equal to 0. In that case, we substitute k into the equation above, and then we get 1 over n theta. If k is equal to 1, then this means 1 over n theta plus 1 over n 2 pi, assuming that we are working in the unit circle. And then this is up to k equals n minus 1. If we substitute it, we get 1 over n theta plus n minus 1 over n 2 pi. In fact, when k is equal to n, we obtain the first solution. And when k is equal to n plus 1, we obtain the second solution, and so on. So we get a repeating sequence. Okay? So it turns out that there are n many nth roots of unity. When I say unity, I simply mean that complex solutions to the equation x to the power n equals 1. Okay. So there are n many complex numbers x satisfying this equation. Okay. Okay, so what is the nth root of unity then? The nth root of unity is c to the power 1 over n. And if we fix the magnitude as 1, in the polar form this is 1, and if the phase is, suppose that the phase is 0, so suppose that rho is equal to 1 and phase is equal to 0, then we have c to the power 1 over n, 1, 0, and this is equal to 1 to the power 1 over n in the magnitude, and in the phase we have 1 over n times 0 plus 2k pi, which is equal to 1 2k pi over n. So by giving k n many different values starting from 0 to n minus 1, we get n many different roots of unity. Okay? By giving n different values to k, we get n many different roots of unity. And as I said, when k is equal to n, we obtain the first root. When k is equal to 1, we obtain the primitive nth root of unity. So when k is equal to 1, we obtain the primitive. This is called the primitive root, primitive nth root of unity. The kth nth root of unity in the exponential form is simply written as, so let's write that, the kth nth root of unity is, in the exponential form, it's e to the power 2 pi I k over n. So since there are n many distinct roots of unity, we denote them by different notations. We use the omega notation. Roots of unity are denoted by omega 0, and this is equal to 1. And then we have omega 1, the primitive nth root of unity, omega to the power 2, omega to the power n minus 1. In fact, the nth roots of unity can also be shown by dividing a unit circle to n equal slices, each of which has an angle 2 pi over n. For example, let's consider the 8th roots of unity. We can show the roots on a unit circle by dividing it by into 8 equal slices. Okay, each with an angle 2 pi over 8. So then we may denote the 8 roots of unity on a unit circle as follows. Suppose that this is our imaginary axis and this is our real axis. So this is a unit circle. So this is 1, this is the primitive root, this is the second nth root, the third, fourth, fifth root, sixth root, seventh root. The eighth root is actually equal to omega to the power eighth, and that's equal to omega to the power 0, which is equal to 1. So note that if we add all these vectors all together, okay, we get 0. They cancel each other. We have that omega 0, which is equal to 1, omega 0 plus omega 1 that's equal to 0. In general, if we multiply the exponent by the factor j, the summation is simply equal to 0, provided that j is non-zero. So provided that j is non-zero, in general, one plus omega to the power j plus omega to the power 2j omega to the power n minus 1 j is equal to 0. And if j is equal to 0, then simply we have that the summation will be equal to n. Then the sum will be equal to n. Okay, another important notion is the conjugate of roots of unity. We know that the complex conjugate of a complex number is simply flipping the sign of the imaginary part. The complex conjugate of a root of a complex number is denoted by the conjugate of, say, omega to the j is omega to the j star. Okay, and this is in fact, this is equal to omega to the n minus j. Right? Okay, so, but we know that omega to the n is equal to 1. We know that omega to the n is equal to 1. So then we have omega to the n minus j, that is the complex conjugate of omega to the power j, is equal to the omega to the power n minus j, and this is equal to, please separate the exponents, omega to the power n times omega minus j. This is 1 times omega minus j, and that's equal to 1 over omega j. Okay? So the complex conjugate of omega to the power j is simply 1 over omega to the power j. In the exponential notation, we know that the kth nth root of unity is the kth nth root of unity is omega to the k, and that's equal to e to the power 2 pi I k over n. So its complex conjugate is omega to the k star, and that's equal to e to the power minus 2 pi I k over 1. Alright, so next we will talk about the quantum Fourier transform.